Hello everyone and welcome to our 7th video lecture. Today we're going to learn about line integrals. Specifically, we'll learn how to interpret and calculate the following two kinds of expressions. The first is the integral of a scalar valued function over a curve C. The second is the integral of a vector valued function over a curve C. We'll also consider analogous expressions in 3 dimensions. As we mentioned in the previous video lecture, the motivation for this is certain classical problems from physics, including the calculation of work done by a particle moving inside a 2 or 3-dimensional vector field. Think about, for example, some sort of spacecraft moving through our solar system. It experiences all sorts of different kinds of gravitational forces depending on what's around it, its proximity to planets, moons, etc. If we're flying from the Earth to the moon, say, the forces that we're experiencing gravitationally are changing over time. Their direction, importantly, is changing as well. The calculation of the work in this instance is telling us approximately how much energy is going to require to make the trip. One could immediately imagine how that might be important to factor in the design of, say, the vehicle. I mean, it'd be really inconvenient to get halfway there and figure out that your vehicle doesn't have quite the mileage you require to make it there and back again. Though, if the Martian taught us anything, this isn't something that can't be corrected by a can-do attitude and a bag of potato seeds. In any event, to start our discussion, I want to think back to something that we covered all the way back in Calc 1, which is specifically how to get the length of a particular curve in the xy plane. The problem is to figure out the length of the curve formed by a graph of y equals f of x between two different values of x. Pictorially, we're trying to figure out the length of the blue curve y equals f of x, depicted in this picture below. The answer that we proved in Calc 1 was an integral, specifically the integral from a to b of the square root of 1 plus f prime of x squared dx. I want to generalize this, starting out, to the situation when my curve is given by some sort of parametric equation. Obviously this can be far more general, because the curves that I get don't have to, for example, pass the horizontal line test, the vertical line test, or anything like this. So we have the following vector calculus version of the question that we stated before. What's the length of the curve described by the parametric equation r of t equals x of t y of t for t between some values, say a and b? Here now, r could be some sort of really crazy curve here, starting at the point r of a and finishing at the point r of b. The derivation of the integral giving us the actual answer here will feel very familiar if you remember the solution in the Calc 1 situation. The idea is the same as before. We don't really know the length of this particular curve, but we do know the lengths of straight lines. And if you zoom in on anything close enough, it becomes something that looks very, very straight. In other words, what I want to do is I want to come up with an approximation where I'm treating my curve as a collection of straight line segments, like so. And if I just continue on, making a whole bunch of line segments, I end up with a red curve, which is very close to the actual blue curve. So the length of the red curve will be about the same as the length of the blue curve. But I can get the length of the red curve because I can just add up all those individual straight length segments, kind of like I connect the dots. If I want an even better approximation, I could just use more dots. And in the limit, as I use as many dots as I possibly can, I get the actual length of the blue curve. So to start out, I want to figure out a formula to get n different dots on my curve. What I'm going to do is I'm going to take my interval from a to b, and I'm going to subdivide this into n distinct intervals. And I'm going to label each of these intervals, or at least the endpoints of each of these intervals, starting with t0 being a, I'll let the next point be t1, then t2, t3, and so on, ending with tn equal to b. For simplicity, it makes sense for these intervals to be the same length, so each one has a width here of some value, let's say delta t. That means that t1 will be a plus delta t. t2 will be t1 plus delta t, so it'll be a plus 2 delta t. I'm going to move over by delta t twice. T3 will be a plus 3 delta t, and so on. So we see here that just tk for any particular k will be a plus k times delta t. Now each of these times is going to give us a point in the curve just by plugging it into r. So r of t1, r of t2, etc. will all be points on my curve. In the picture, the starting point is r of t0 because t0 is a. The next point that we get there is going to be r of t1. The next point will be r of t2, etc. So the distance of the line segment, or the length of the line segment between those 2 points, is just given by the distance formula. Or alternatively, it's just the magnitude of the difference of those 2 vectors. It's the square root of the sum of the squares of the differences of the entries. So our estimate using n length segments is just the sum of the n individual line segment lengths, so the sum of these square roots. And now what I want to use here is that for delta t very small, x of tk minus x of tk minus 1 is about the same thing as x prime of tk times delta t. Similarly, y of tk minus y of tk minus 1 is about the same thing as y prime of tk times delta t. So with this, our estimate using n segments becomes, and for shorthand, let's just call that Sn. So Sn becomes the sum from k equals 1 to n of the square root of x prime tk delta t squared plus y prime tk delta t squared, which simplifies to the square root of x prime of tk squared plus y prime of tk squared, all times delta t. And if you recognize this, this is a Riemann sum. So if I take the limit as n goes to infinity, that is, as I choose more and more line segments, I actually end up with the real length of that curve, and it's equal to that sum, but the sum sign now becomes an integral because I'm adding up these infinite many components from the starting point to the ending point, so from a to b, of the square root of x prime of t squared plus y prime of t squared, and then the delta t becomes a dt. So this is our answer in Calc 3, or vector calculus. You notice, as a special case, when r of t is t f of t, this just traces out the curve given by y equals f of x from a to b. And the equation there is the integral from a to b of the square root of 1 plus f prime of t squared dt, which is exactly the equation that we got before in Calc 1. So this is a complete generalization of the previous case. Notationally, we write ds to mean the square root of x prime squared plus y prime squared dt. This describes a specific differential called the arc length differential. Then the actual arc length of that parametric curve is given by the integral from a to b of ds. More generally, we can define the arc length function. The arc length function of a parametric curve, r of t, defined for t between a and b, is given by s of t, which is equal to s of t, which is the integral from a to t of ds, or equivalently, the integral from a to t of the square root of x prime of u squared plus y prime of u squared du. So what s of t represents is the arc length of the curve defined by r of t from t equals a all the way to t equals t. In particular, s of b is the full length of the curve. Now let's think about the following problem. Suppose I have a length of wire which has a non-uniform linear density. So how dense it is at one particular spot in the wire is different from another spot. And my problem here is to calculate the total mass. How do I go about doing this? My wire can be specified by some sort of parametric equation. And then to specify the density of the wire at any particular point, I can describe the density at the corresponding x and y value. In this case, the total mass of the wire is going to be given by just adding up these infinitesimal little segments of wire times the local density. In other words, it's given by integrating the density at some particular point in the wire times the local infinitesimal length of that line segment, like so. We rewrite this expression as the integral of rho of xy times ds. So this is our very first interpretation of a line integral. In fact, this sort of intuitively motivates our definition for any particular function. Let c be a curve, and let f of xy be a continuous function. Then the line integral of f of xy on c, which is this expression here, is given by the integral from a to b of f of x of t y of t times the square root of x prime of t squared plus y prime of t squared dt. Where here, r of t equals x of t y of t is some parameterization of c. And there are some important points here we should go over. The curve should be a smooth curve. That is, we don't want any like crazy jagged jumps and strange things happening. It needs to be something which is sufficiently nice, no crazy kinks. Otherwise, we might also have problems taking the derivative of the corresponding parameterization. Furthermore, I'm a little bit worried about this definition even making sense at all, because we've defined it in terms of some random parameterization that we've chosen, but it turns out that this is independent of whatever parameterization we choose. We just need to pick one. And it's good to remember that for any particular curve C, there are lots and lots and lots of different ways to parameterize it, infinitely many different ways to parameterize it. So this is an important point to think about. But it turns out that this calculation is entirely independent of the parameterization we choose. This makes some sense intuitively, because if I'm thinking about this calculation as giving us something like the mass of that wire, it should be completely independent of how I parameterize the description of the wire, right? The wire's mass is something which is intrinsic about the wire itself, not about the way that we're describing it mathematically. And one further thing I'd like to point out, which sort of makes the notation a bit nicer, is we can rewrite this as the integral from a to b of f of r of t, which takes t to x of t, y of t, to f of that, times the magnitude of the vector r prime of t dt. So that's a nice way to remember exactly what calculation we're doing in sort of a nice vectoric way. Since we're doing vector calculus, I feel like that's a very appealing thing here. And you can go ahead and double check that my blue expression here is exactly that integral that we were doing before with the square root and everything, because that's how the magnitude of a vector works. So let's go ahead and do an example. In this example, let's let f of xy be equal to x squared y, and let's let c be equal to the arc of the unit circle in the first quadrant. The first part of this problem deals with actually coming up with a parameterization of the curve that we're considering. This is the curve C, which I've drawn on the xy plane in red in the picture. Now, part of the definition was I can choose any sort of parameterization that I want, and I can still get the correct answer, but I want to choose a parameterization which is going to make my life easier. And one of the easiest ways to parameterize some sort of circle type experience is to use sine and cosine. So the parameterization I'm going to choose is I'm going to let r of t be equal to cosine of t, sine of t. And if I let c wander from 0 to 2 pi, I'm going to get too much. I'm going to get the full circle of radius 1. And I just want that part of that unit circle in that first quadrant. So I'm going to bound t between 0 and pi over 2. So this is a nice parameterization of that curve C. And then the calculation I want to do here is I want to calculate the integral over my curve C of f of xy ds, that first line integral. Now again, intuitively, if f of xy is the density of some sort of wire in the shape of the curve C, this would be calculating the mass of that wire. But from our definitions above, this is going to be the integral from 0 to pi over 2 of x squared y, but I'm going to fill in my x value and my y value, so it's going to be cosine t squared sine of t times the square root of x prime squared plus y prime squared. X prime squared is minus sine, so I'm squaring that, so I'm going to have sine squared, and y prime squared is going to be cosine squared, dt. And we can already see that something kind of magical is happening there. Sine squared plus cosine squared is 1, so this is the integral from 0 to pi over 2 of cosine squared t times sine of t times 1 dt. And to do this integral, we can just do a nice U-substitution. We substitute u equals cosine of t, so du is minus sine of t dt. And this integral becomes the integral of minus u squared du. And my new bounds are 1 and 0. So if I calculate this integral, this ends up giving me 1/3. Great. Let's do another example. Here I want to calculate the integral over c of x over y ds, where here c is the curve y equals x to the 4 over 3 between x equals 1 and x equals 8. We can come up with several parameterizations of the curve in order to calculate this line integral. One example is taking r of t to just be t to the 4 over 3 between t equals 1 and t equals 8. We can see that this parameterizes exactly the curve described by this function. Let me actually specify that this is that particular curve. C is the curve given by this equation. Then the line integral that we want to do becomes the integral from 1 to 8 of x over y, which is going to be t divided by t to the 4 over 3, of the square root of x prime squared, which is just 1, plus y prime squared, which is going to be 16 over 9 times t to the 2/3 power. This is equal to the integral from 1 to 8 of t to the minus 1/3 times the square root of 1 plus 16 over 9 t to the 2/3 power dt. And now I can do a U-substitution. I'm going to substitute u equals 1 plus 16 over 9 t to the 2/3. So the du is equal to 32 over 27 t to the minus 1/3. Our integral then becomes the integral of 27 over 32 times the square root of u du. And the new bounds of the integral are given by 25 over 9 and 73 over 9, which is 9 over 16 u to the 3 halves, evaluated from 25 over 9 to 73 over 9, or approximately 10.3898. We can do several similar line integrals in 3 dimensions. For example, I can think about a curve C in 3 dimensions, starting from a certain point and ending at a certain point, and I could ask questions. For example, what is its length? Or if it has a non-uniform density, what is its mass? And we should be able to do the same sort of calculations and similar line integrals in order to get the answer. In particular, if this is parameterized by an equation r of t equals x of t, y of t, z of t, for t between a and b, this means that the beginning point is r of a, and the ending point, of course, is r of b, and the length of the curve is given by the integral from a to b of that arc length. But in this case, the arc length is the same as before in terms of the vector notation. So it's the magnitude of r prime of t, just like before. The difference now, and I guess I shouldn't write here a to b, I should write here the curve s, or c. But the difference here is that r prime has three different components. So this is the integral from a to b of the square root of the sum of the squares of the components of r prime. So it's going to be x prime squared plus y prime squared plus z prime squared dt. And more generally, we can define any line integral in 3 dimensions very similarly to the case of 2 dimensions. So the line integral of some function f of x, y, z on a curve C is just denoted exactly the same way, and it's going to be f of x of t, y of t, z of t times the square root of x prime of t squared plus y prime of t squared plus z prime of t squared dt, evaluated from a to b, where here r of t for t between a and b is just a parameterization of the curve C, and again this is independent of the parameterization. And also, just like before, notationally we may write this as the integral from a to b of f of r of t times the magnitude of r prime of t dt. And I think that's the power of this vector notation, is that this is the same formula, that blue formula there, regardless of whether we're in 2 dimensions or 3 dimensions or what have you. And as far as what this is intuitively, again, we're thinking about this as being some way of, if f of x, y, z is the linear density of this wire, this is adding up all those different density elements and giving us the total mass. This is also a really intuitive reason why this should be independent of the parameterization, because all the parameterization does is describe what the wire is and what its positions are in some sort of coordinate system. So if we describe it in a slightly different way, different parameterization, it doesn't change the wire, so it shouldn't change the mass. For example, let's calculate the integral of x squared plus y squared plus z squared ds, where here C is the helix, described by the parametric equation r of t equals cosine of 2t sine of 2t t for t between 0 and 2 pi. So it's kind of interesting if we draw a picture of the curve that we're integrating over. It starts out at the point 1, 0, 0 and spirals up like a spring all the way to the point 1, 0, 2 pi. So this is a pretty neat curve to be integrating over. And our formula is really easy to remember. All we're going to do is we're going to calculate the integral from 0 to 2 pi of our equation, and I'm going to substitute in the parameterization, so it's going to be cosine squared of 2t plus sine squared of 2t plus t squared. That's the same thing as x squared plus y squared plus z squared with this particular parameterization. And I'm going to be multiplying this by the square root of x prime squared, which is going to be minus sine, but I'm squaring it, so it's going to be sine squared of 2t times 2. So it's going to be 4 sine squared of 2t plus 4 cosine squared of 2t plus 1. This is integral with respect to dt. And this is now going to become, if I remember that sine squared plus cosine squared is 1, this becomes the integral from 0 to 2 pi of 1 plus t squared times the square root of 4 plus 1 dt. which is a very easy integral to do. This is t plus 1/3 t cubed times the square root of 5 evaluated from 0 to 2 pi. So our final answer is 2 pi plus 1/3 the quantity 2 pi cubed times the square root of 5. We can also define line integrals along curves with respect to x, y, and z. For example, the integral over a curve c of f of x, y, z dx means we just do the integral from a to b of f of x of t, y of t, z of t, times x prime of t dt, where here x of t, y of t, z of t is that parameterization of the curve c, and again this is some quantity which would be independent of the parameterization. We can similarly define integrals with respect to x, or y, and with respect to z in the most obvious way, where here, once more, r of t is just that parameterization of the curve c. R of t equals x of t, y of t, z of t. So these are nice straightforward things to do. So we've got 4 different sort of line integrals now. The line integral with respect to arc length, ds, as well as the line integrals with respect to dx, dy, and dz. For example, let's calculate the integral over c of y dx plus z dy plus x dz, where here c is the curve parameterized by x equals the square root of t, y equals t, and z equals t squared for t between 1 and 4. Our definitions from before tell us that this is just the integral from 1 to 4 of y times x prime of t dt plus z times y prime of t dt plus x times z prime of t dt. This is just the same thing as the integral from 1 to 4 of y times x prime. X prime here is going to be 1 over 2 times the square root of t, and y itself is t, so this will be t times 1 over 2 times the square root of t dt, and I'm going to pull all the dt's all to one side here, plus z times, and z is t squared here, so t squared times y prime, which is just 1, plus x, which is the square root of t, times z prime, which is 2t, all times dt. So it's that simple integral here, which is just the integral of 1/2 t to the 1/2 plus t squared plus 2t to the 3/2 from 1 to 4, which is a very easy integral. It's just 1/3 t to the 3/2 plus 1/3 t cubed plus 4/5 t to the 5/2 evaluated from 1 to 4. And I'll let you guys at home finish that off. Now, one of our main motivations for studying line integrals is to do calculations involving things like force and a particle moving through a force field and calculate the amount of work done. So if I've got a particular force field in the xy plane, let me just draw one for us. This is a picture of the force field F of xy equals x over the square root of x squared plus y squared, comma, y over the square root of x squared plus y squared. And I'm thinking about maybe some particle here, which is wandering through this force field. Let's take a blue particle here, and let's say that the blue particle moves in a perfect circle around this way. See if I can draw a circle from my starting point to my ending point. If I'm thinking about how it works, how work works, for example, if I'm doing work against the field of gravity and I move an object like a bowling ball or something, when I move that bowling ball up vertically or lower it down vertically, then I'm doing work. But if I'm moving that bowling ball sideways, it's not being opposed by the force of gravity, so I'm not doing any work in that case. And here you can see that the trajectory of my particle is always going to be orthogonal to the local vector field. So it's never opposing the vector field, and intuitively here we would expect no work to be done. So my blue particle is a very lazy particle. It goes from its starting position to its ending position without doing any work at all. However, if I look at the trajectory of this green particle from its beginning to its end, at some point it is actually opposing the local force field. It's going against it, and so work is being done. To figure out how much work is done, what I want to do is I want to figure out the component of the local force field in the direction that the particle is moving at any particular point in time. And that's exactly done by using the dot product. So if my particle's trajectory as a function of time is given by r of t equals x of t, y of t, from some starting time a to some finishing time b, then the work done is going to be the integral from a to b of the local force field at some particular value, which is just f of x of t, y of t, which is a vector here. And I'm going to dot product that with my local tangent vector to my curve at that particular t value. And I'm going to multiply that by my little arc length element, which I remember is given by the magnitude of r prime of t dt. And if I add all that up, I get exactly the amount of work done. But now I want to remember that the local tangent vector here, t of t, this is given by r prime of t divided by the magnitude of r prime of t. This is something that we calculated back when we were thinking about parametric equations. So this equation becomes the integral from a to b of f of x of t, y of t, times, well, dot product specifically, with r prime of t dt. So it's a very easy thing to calculate here with this dot product. And very nicely, we don't have the magnitude of r prime in there anywhere, so it's getting rid of the radical expression as well that we typically see, which is really very convenient. It makes a lot of these integrals much easier to evaluate. So this motivates the definition of the line integral of a force field, a vector field along a smooth curve. We express it as the integral over c of f dot dr, where these are both vector symbols, so their dot product is going to be a scalar in the end. It's very important here when we're calculating these integrals, we're getting a number out in the end, not some sort of vector expression. And this is going to be given by the integral from a to b of f of r of t times r prime of t dt for any parameterization r of the vector field. So where here r of t equals x of t, y of t for t between a and b parameterized as c, and we can also do a three-dimensional version, and the equations above here aren't changing at all. The only thing that's changing here would be my expression for r would then have three components, and then the dot product that would be taking is the dot product of vectors which have three components as well. And again, intuitively, we should think about this as the amount of work done by a particle moving along the curve c experiencing a force described by F. So it should be some sort of intrinsic thing which is independent of the parameterization, the way that we're describing the curve in terms of some parameter. Let's look at an example of this. If you think about a vector field F of xyz given by f of xyz equals x plus y squared xz y plus z. And let's think about calculating the force experienced by a particle in this force field moving along a trajectory parameterized by t squared, t cubed, and minus 2t. The answer is very easy. All we're going to do is just calculate r prime of t, which is just going to be 2t, 3t squared, and minus 2. And I'm going to take the dot product of r prime with f. F here, we're going to evaluate an r as well. So f of r of t is the same thing as f, but with my x, y, and z values all replaced by their corresponding t values. So it's t squared, plus t cubed squared, so t to the 6th, t squared times minus 2t, so minus 2t cubed, and finally t cubed minus 2t. And I just take the dot product of these two expressions, and my integral that I want to calculate, integral over c of f dot dr, is just going to be the integral. Oh, and I left out some information here. I want not just some curve with unspecified beginning and end, but I want to have it bounded by, or starting at t equals 0, and ending up at t equals 2. So then my integral is going to go from 0 to 2, and it's just going to be the dot product of these two expressions. So it's going to be t squared plus t to the 6th times 2t plus minus 2t cubed times 3t squared plus t cubed minus 2t times minus 2 dt. And this is just a very nice, easy polynomial integral to evaluate, so I'm not going to bother to do it here. You guys can definitely do that one at home. But this also demonstrates here how much nicer maybe these line integrals of vector fields are compared to maybe their counterparts for the scalar case when we have to deal with this arc length expression, which has that radical and everything. And generally those integrals with that radical can become quite a bit more complicated and may involve U-Substitution, that sort of thing. Or maybe are even worse and can't be done by hand if we're not carefully choosing them. But this is a pretty good place to stop for our lecture. So we've, just as a recap, we've defined line integrals of scalar valued functions, both with respect to arc length ds, as well as with respect to dx, dy, and dz. And we've also defined line integrals of vector valued functions. And we've done this in both 2 dimensions and 3 dimensions. We're going to explore this further with our future lectures, and in particular we'll be thinking about how the properties of the vector field might influence these line integrals. You know, in particular, some of these very natural vector fields, the ones corresponding to gravitational fields and these sort of things, are going to be conservative vector fields. And when we integrate things with respect to conservative vector fields, some very nice things are going to happen. In particular, we're going to have some independence properties, where it's not only going to be independent of the parameterization of a curve, it may also be independent of the curves that we choose themselves. So it'll just be dependent on the beginning point and the end point of things, which is a really interesting property to have. You can kind of think of it this way. If I'm thinking about how much energy it's going to take to walk from the bottom of a hill to the top of a hill, in terms of the total energy done, it doesn't matter what route I take to go up the hill, because every time I go down, I am doing negative work, and every time I go up, I'm doing positive work. So it all sort of comes out in the wash, and it just matters how high I ended up with in the end, because the total work done is just the change in potential energy, and the potential energy that I'm at depends on my height. So things like this are going to give us some really nice ways to calculate these line integrals, and more generally for non-conservative vector fields, we'll be able to appeal to something called Green's theorem, and that'll be very fun too. So we'll be discussing all those things in more detail over the next few lessons, and I will see you guys there.